I'm going to start today by kind of trying to introduce AI from a non-technical perspective. Let me also say why we decided to do this session. Two reasons. One, as you know, this university has many other disciplines besides AI, including energy science, life science, e-mobility, and going forward, we'll also have sustainable entrepreneurship. Now, even though we are trying to get AI as a minor available for all majors, we wanted to kind of use this opportunity to create a non-technical introduction to AI for two reasons. One, so that folks who are not from a computer science or an AI background have some broad themes on how this field has evolved and where it is going. So that was one reason. And second, of course, we realized that even with students who do enroll for DT and AI as a major or minor, by the time they come to appreciate what this field is, they are in their final years, right? It takes a long time to go through the history of how this field has evolved, because we are teaching them each subject, we are teaching them each theme as we go along. So we wanted to try something different. We wanted to flip it and say, can in 1 hour or 2 hours, we can give you an overview of the field without the math, without the computer science, so that you know the big picture, right? That's really what we are trying to do today. And that's the objective of the talk, right? So today is Friday, 6th February, and we are doing a talk called The Brief History of AI. We will cover the evolution of AI from the 1940s right up to 2010s, right? Next week is post-2020 AI. Post-2020 AI is basically what most of you are familiar with, whether it's ChatGPT or Gemini or Claude. All that kind of falls in post-2020 AI. So that will be Friday, 13th Feb, 1 week from now, again 12 to 1. So that's the second part of this talk, but it's important to kind of start with the history. So we are starting with the history today, right? And this is my first overview slide timeline. This is also the last slide that I will put so that you know, probably understand the slide in a different way. So if you look at the history of AI, we'll broadly start from the 1940s, right? And 1940s is not incidental. It was the Second World War, right? And as you know, a lot of technologies get invented because of the defense and research departments funding going into defense departments funding it. And that's the reason the story really starts in 1940s, and I'll talk more about that as we go along. But it was really in the 1940s that we started asking, can machines be intelligent? Right? And as you will see, the thing that happened during this time was that intelligence was defined in terms of being able to use language, which is English words, or math, which is symbols. And the idea was, can machines manipulate words and symbols just like humans can? And that was the first era of intelligence in machines. In 1970s, we see the emergence of a different kind of AI. This is more inspired by games, right? How games are played, typically tic-tac-toe, chess, and also robots comes into play here a little bit. And this is basically talking about logic as intelligence, right? And you kind of start to know the idea of state space, which I will introduce briefly. But you start thinking about logic being the ability to apply logic as intelligence. Then during the 1980s, the field shifts, and we realize that logic is not sufficient. And we talk about knowledge as intelligence. And this leads to this whole era of things like knowledge engineering and fuzzy logic, which emerges during knowledge as intelligence period. Then in the 2000s, we see learning as intelligence, right? And this is really the era of data science, right? The idea that data science is the sexiest job of the 21st century appears during this time. It's a fundamental shift in the journey of AI, but now we are thinking about learning as intelligence. And the last part, which we will only briefly talk about today, we'll talk about a lot next time, is the idea that can we create an artificial brain, right? So the brain as a paradigm of intelligence, right? And this is it starts in 2010s, and it really comes to full power in 2020s, right? So this is the history of AI as I will cover it. As I said, I will also flash this slide towards the end after having gone through each one of these eras so that you kind of understand it. But that's, if you're going to take away one slide from today, it is this slide. Right? That's what should sit in your mind. Okay, so let's start with the first era. Right? Now, the history of the first era can actually be traced much, much further back, to a German mathematician called Leibniz, who also worked on a variety of problems. But he was the first person to kind of ask the question that can there be a universal language for science and math, right? A universal formal language. And if two people are talking to each other and they don't agree with each other, can you have a machine resolve the differences between the two? Right? So can you actually bring in machines who is all human conversation fundamentally calculatable? Can you calculate all kind of human reasoning, logic, right? So he's the first person to put this argument forward, and he does it using pictures. So the picture that you see actually comes from his writing. And this is a time when the theory that the universe is made up of earth, fire, water, and space, and he's trying to say that if the whole universe is made up of these fundamental earth, fire, water, space, then arguably all knowledge, all intelligence, all thought is also made up of earth, fire, water, space. So then can we have the fundamental language of logic or thought? And he's the first person to put it forward, and he proposes this idea that there is something called a universal language, which is calculable, and therefore you can create a machine which can calculate human thought, right? And if you were to say it in one idea, he comes up with the idea that all reasoning that humans do when they talk to each other is calculatable. You can calculate reasoning, right? So he conceives of this idea that all logic can be calculated or computable, right? Now, this is not very far from reality. For those of you who have studied Boolean logic, right, 2 centuries later, 200 years later, Thomas Boole creates Boolean logic. And Boolean logic is that, if you think about it, Boolean language, all computing today is based on Boolean logic. So in fact, in 200 years, the fact that we could come up with a universal language in which everything can be computable and calculatable is extremely fast progress. Right? So think about, the idea emerges in 17th century, and by 19th century we have invented this Boolean logic, which says all logic is computable, all reasoning is computable, right? In some sense, this is the origin. This is the origin of intelligence. This is the origin of computability, right? Now, the way this gets realized, right? That was a concept. So that was in the 17th century. The way that gets realized is during World War II. And again, the innovation comes from Germany, right? And the innovation that comes is this machine, right? If you have seen a movie called The Imitation Game, right? It's a Hollywood movie. This is a machine that was called the Enigma machine. It was invented by the German military. And what it used to do was it allowed German soldiers to communicate secretly. So you could type in a message, and the message was transmitted wirelessly to all the other German units who were in the field fighting the enemy. But it was encrypted, right? So it's the first encrypting machine. So the message was secret. So even if you could hear the message, you would not be able to understand it, right? This is called the Enigma machine. This was invented by the Germans, and it could take a message and encrypt it, make it secret in 150 quintillion ways, right? So it was extremely hard for the armies which were fighting the German army to break this code, right? Now, the way it was traditionally done was there are armies of people who were very good at solving crossword puzzles, trying to solve these puzzles and trying to break the code. It was Alan Turing, a British mathematician, who came up with the solution. And he created the machine on the right. And this machine was called the bombe, right? B-O-M-B-E. And the bombe machine was an electromechanical device which succeeded in cracking the code of the encrypted message which the Germans were sending. So the Germans were sending these encrypted messages using a machine, and the Britishers, led by Alan Turing, built another machine to crack the code, right? Now, take a moment to think about what just happened. a job which was being done by an army of puzzle solvers and crossword solvers is now being done by a machine, right? And this machine, of course, used math and used some insights on how the messages were sent to be able to solve this problem, right? But this is also a landmark in the history of AI because you now have mechanical intelligence. You have machines which are solving puzzles. Right? Think about cracking cracking the code or trying to decrypt a message without knowing the secret is like solving a puzzle. So this is the first time that you have demonstration that a machine is able to solve a problem which humans are not able to solve at the speed at which we want, right? So this instance you can think of as the first landmark, right? Now, if you look at it from a math perspective or a computing framework perspective or theory perspective, right? The next question that came up once these machines were invented was what kind of problems could be solved by machine, right? Are all kinds of problems solvable by machines, right? And that was the questions that led to the whole something called theoretical computer science, right? So I'm not going to go into theoretical computer science, but there's this whole field of computer science which asks what is computable? What can you solve using computing? And that field continues to exist today. Then you also have at this time people asking what is intelligence? And till about 5 years ago, the gold standard on what is intelligence was called the Turing test. And it was also created by Alan Turing. And the Turing test basically was this thing, which the test was as follows. It says, the question was, how do you know that a machine is intelligent? When do we say that a machine is intelligent? And the Turing test was proposed in the following way. Suppose you are a human, and I put a screen in front of you, which is you cannot look through who's on the other side. And on the other side can be a machine, or it could be a human. And you are supposed to talk to it. And you are talking to it, and if a human is talking to somebody on the other side of the screen, and the human cannot tell whether the person on the other side or the entity on the other side is a human or a machine, then you have achieved intelligence. Because if you can't tell whether the person you are talking to is human or machine, then we have achieved intelligence. That was the Turing test. And till about 2018, 2019, it was considered the gold standard on saying, are machines intelligent or not? And all of you today use ChatGPT, so Turing test has been passed much ahead of time. So the Turing test has been passed. Of course, since then we have changed the definition of what intelligence means, but this was the gold standard in intelligence for several years. It is during these times, during the 1940s and 50s, that another field of AI and computer science gets invented, which is what is information, right? And for those of you who have studied machine learning or AI, we continue to use these ideas. If you know of an algorithm called decision trees, it still uses the ideas that were introduced during this time by Claude Shannon on defining entropy and defining information. So the fundamental ideas are born in the 1940s. What is computing? What is intelligence? What is information? And all of these became the bedrock on which AI evolved. And all of these are mathematical formal things, which of course I'm not going to go into today, but that's the mathematical framework on which this is built, right? Now, what was the problem? Of course, this field lasted about 20 years. The first big problem that researchers ran into was that they underestimated how complex the real world was, right? So for example, if you look at chess, right, which is for the longest time till 1990s, this was another paradigm of, or another milestone. Can a machine beat humans at chess? So it was considered a milestone in intelligence. In 1998, of course, we know IBM Deep Blue beat the humans at chess. And today, there is no human who can outperform a machine playing chess. But at that time, the bottleneck was that chess was considered an extremely complex game because the number of potential moves that you could make and the number of potential ways that the chess could play out was so large that the machines that were being built at that time were not able to navigate that space, right? So they underestimated the computational complexity of something which we feel today is as simple as chess. Okay. The second thing that, another example of this is in Dartmouth in 1956. This is the group of people that you see in 1956 These are the people who termed the coin AI. The first time you hear the word AI, artificial intelligence, is proposed by these people. This is Marvin Minsky. You can see Claude Shannon, many other mathematicians during that time. Just to give you an idea, in 1956, they submitted a research project saying that we will build an automated machine translation from English to German and we'll finish it in 3 months, which is still not done. You still don't have translation which is perfect. So the idea is, the reason I'm telling you this is that the complexity of achieving intelligence was extremely underestimated. People thought they'll be able to solve it in a few years, and almost 100 years later, we are still sitting here. Okay, so that was the first phase, the philosophical computing underpinnings of where AI was born. Right. The second era, which begins in the 1950s, World War II is over, right? And we are kind of in an era in the West where we are looking at innovations. And this comes with, as we said, logic is intelligence. And this gets motivated by games, right? Can you have a game playing machine? And the simple example here is tic-tac-toe, right? So let's suppose everybody has played tic-tac-toe, crosses and circles, right? So suppose you are sitting here. The question that they posed is, can the machine know what move to make next? Right? That was the question, right? It seems like a logical argument. So can the machine logically deduce, can the machine know what is the best move to move next? So in this case, as you can see, there are 3 moves that you can make next, right? But to decide which move to make, the machine then has to think logically as to, if I make this move, what is the next move that my opponent will make? And then if they make this move, what is the move that I will make? And then if I make that move, what is the move that they will make? So that the ability to logically argue through this sequence and decide what is the best step right now became the foundation of logic. And people tried to write algorithms which encoded this logic. And this general principle more generally became known as the state space approach. What that means is that the game is in this state, and the final state you want to reach as a machine playing a game is you want to win the game. So how do you go from the current state of the game, which is this, to a state where you win the game? So the intelligence became, how do I navigate the state space? How do I change the state so that I eventually win the game? The same thing also started leading to robotics, right? The first robots were built during this period, right? And I'll show you an example of a robot. But a robot, again, is an example of a state space. So if a robot, let's suppose you expect the robot to enter that room, come here and switch off this laptop. It's a very complicated problem, right? Because the laptop first needs to know what is in front of it. It needs to be able to see the chairs. It needs to be able to see the table. It needs to be able to see the laptop. Then it needs to decide, how do I move so that I don't bump into everything? But the end idea is that if you want to move from this point to this point, you need to know how to turn, you need to know how fast to go, and you need to find the best path. For example, if the robot is moving and I put a chair in its path, then it needs to be able to adapt. It needs to figure out how to navigate the state space which is changing. Okay, but the fundamental idea of intelligence during this time was not the way, remember in the first era it was cracking the code of Enigma and the bomb machine. Here it was about navigating the state space. How do I get from point A to point B? Point A, point B being physical points or virtual points in the state space of games, right? And the way researchers started working on this problem was to figure out, how do you navigate this search space? How do you decide which action to take next? How do you decide which state to go in next, given that you're sitting in this state and eventually you want to get to a state where you win the game, right? And the project that started in Dartmouth, remember the people who coined the term artificial intelligence, right? They started working on writing very, very long if-then-else statements, right? For anybody who has done programming, if-then-else statements are the bread and butter of early programs. And intelligence started to be coded in these if-then-else statements. Okay, this is the first robot, right? You can actually see this. It's in the history of computing.
near San Francisco. If you look at what's going on in this robot, you'll see there's a camera here, there are wheels here, there are these things, the bump sensors, which detect whether you're bumping or not. Interestingly, this robot did not have a brain inside it. The brain was a separate, very powerful computer which was sitting somewhere else, right? Because it was very large, right? Those days, computers used to be very large. So the computer was somewhere else, but this was the robot. And what this robot used to do was it used a video camera to record and understand where it is in the room, right? So it had to understand where it is in the room. It needed to understand not only from a location perspective, but also from a depth perspective. How far am I from a particular wall, right? Is there something near me? So there was this look at a room. Then it had to figure out, just like if you look at the floor below you, the floor is divided into grids, right? Because of the carpet. So it needed to figure out which grid I am at and which grid do I need to go to. And then it had to figure out how do I get from this to this, which is what action should I take to get from grid A to grid B. Okay. And some of the things, and this is a theme that you will see, all the innovations that were initially made, they don't disappear. We continue to use them. For example, the algorithms that were implemented and invented during this time, breadth first search, depth first search, and A-star search, today are the ones sitting in your phone when you use Google Maps. So in Google Maps, when you say I want to go from point A to point B, the same algorithms help you navigate how do you get from point A to point B. Okay, so the work is still relevant. Okay. If you look at the mathematics frameworks that gets used during this AI era, the 1950s to 1970s, formalization of logic, right? Language gets invented as logic, right? And this is based on a very interesting collaboration between the language departments in the universities, the English departments in the universities. Noam Chomsky, of course, is a very famous linguist, but it's a collaboration between the math department and the English department. And they basically come back and say, can you encode every English language sentence in a mathematical language? And that mathematical language comes to be known as first order logic, right? So for example, here is an example. English sentence is all humans are mortal or all humans die. The second sentence is Bob is human. Since all humans die and since Bob is human, the machine can now conclude that Bob will die. So this is logic, right? A plus B, and you can make inferences from logical statements. In the mathematical language, this is the mathematical language in which sentences like this are written. Of course, this language is much more complex and it has evolved over long periods of time, but logic is a field that continues to live, and that is another innovation that has survived. Okay. The problem that these guys ran into was that these machines where you were encoding first order logic did not have common sense. Now, what is common sense? Right? Common sense is very, very obvious to us humans. Right? For example, I know that if I come here and hold this laptop and pick it up, the table underneath will not move. That is very obvious to us, but it was not obvious to machines. So the machines had to be told every single thing, right? And the amount of knowledge that needed to be told to machines for them to actually build functioning robots of game playing stuff was very, very complex. And they just could never put all the information in a machine, right? And this continues to be a problem for us even today. So there's a whole field of AI which still works on trying to encode human knowledge in some form or the other, whether it's predicate logic, the kind of example that I showed you, or ontologies that we talk about. This continues to be a problem for us. The second very interesting thing that these folks realized was what they thought was the most difficult thing to achieve using intelligence was actually really not. So you could actually build a machine which could play chess reasonably well, but it was extremely hard to build a machine which could walk. So the definition of intelligence changed, right? We thought playing chess was a hugely intelligent thing, but it turns out that being able to walk in a room was very hard. The ability to recognize, I look at you and I know who you are, right? But machines and computers and robots found this to be an extremely hard problem. right? Face recognition was an extremely hard problem, which to some extent is solved now, but not completely. But the definition of, again, what is it to be intelligent was challenged again during this time. Okay, so that was the second era, primarily driven by games, trying to create a mathematical language based on logic and implementing that logic in computer code. Right? We then came to the third era. This is the 1980s to the 1990s, right? And this is called the expert systems era. And in this era, what they realized was that logic was not enough. Logic was not enough. They needed knowledge, they needed encoded knowledge, they needed to document knowledge. And this is during the time you will see a lot of work on what is called knowledge engineering. So what was knowledge engineering? What they realized was that they hired a human to go and talk to an expert. So for example, if you wanted to build a medical AI, there'll be a human who will go and talk to a doctor and spend 5 days with him, asking them all kinds of questions. And they will document all this knowledge in some knowledge database or knowledge repository. If you wanted to build a legal AI system, you would send a person to talk to a lawyer and spend 5 days with him, interviewing them and asking them all kinds of questions and document it in some sort of a knowledge base. And same thing for every profession. So this was the era of specialized AI, where you interviewed a human expert, documented all that knowledge in some sort of a database, and then allowed humans to use it, right? And one of the best example of this is from 1976, right? This was a tool called Mycin, which was built at MIT for doctors, right? So what they did was they picked a very, very narrow problem, right, of identifying what infection somebody has and what antibiotic to prescribe to them, right? And they talked to several doctors, and based on talking to several doctors, they came up with about 600 rules. And these 600 rules were encoded in some sort of a computer program. And these rules look like this, right? If the strain of the organism is blah, 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 then this is the antibiotic to recommend. Right? So they came up with these 600 rules. And then what they said is that if a patient walks in, right, and a physician or a doctor is talking to them, let the physician or the doctor feed in all the information about the patient, including the symptoms, including the lab results and lab tests, and this machine will tell you what is the infection and what is the antibiotic to be prescribed, right? So this is a good example of knowledge base, where you talk to the best people in the world, encode their knowledge in a knowledge base, which allows anybody, quote unquote, to play the role of a doctor, right? So this approach, if you look at what is the mathematical framework here, it's still if-then-else rules, which was still true in the 1950s, but now if-then rules are combined with probability, right? Because you are giving some sort of probability. At that time, they called it certainty factor. So you can say with 80% probability, I'm sure that this is this bacteria. So that was the innovation from a math perspective, that logic, which was if-then-else rules, combined with uncertainty, which was at that time called certainty factor, but was basically a kind of probability. So these two things started to come together. Okay, what was the limitation and why this did not work? The problem is that I don't know how many of you have seen this kind of a 2x2 before, but the problem is most experts don't know what they know, right? So if you try to interview an expert, even if the expert answers every single thing that you ask them, there's a lot of implicit knowledge that experts have, which you will not be able to capture, because they themselves don't know what they know. And if experts don't know what they know, then there is no way you can capture everything by talking to them. So a vast amount of knowledge is implicit, and even experts cannot articulate or tell you why they do some things, right? That was the problem. And if that is a fundamental problem, knowledge engineering will only take you so far, right? The second problem was these systems were very brittle. They used to break very easily, because if the user did not input the things in exactly the right way, the system will not work. The third problem was that knowledge is not static, right? Knowledge evolves. Somebody finds something new, somebody publishes a research paper, somebody makes an advance in science. Now, every time knowledge changes, you have to go back and reprogram the whole thing, right? Because the knowledge base itself has changed, right? So those are the problems with the 1980s, 1990s era. Okay. The next era, and this is the era that I grew up in, is called the statistical learning era. Right? And if you look at our curriculum, this is where we start. Right? Most of our curriculum, when we teach AI and machine learning, we start here without telling you the history, which perhaps, hopefully, will not be a problem going forward because this talk is being recorded. Right? This was a paradigm shift. This was a paradigm shift in 1990s. And the reason is that the approach to intelligence changed. So if you look at all the history of computing till 1990s, right, we were giving machines very, very specific instructions. Those instructions were in the form of if-then-else rules, knowledge bases, confidence scores. In 1990s, the approach completely changed. They said, we will stop telling computers what to do. We'll stop programming computers. Rather, we'll just feed a lot of data to computers and let them learn. Right? So you were teaching the machines using data. It was not programming the machines to embed the knowledge that we already know into the machines. That's not what it was. Right? This is the reason why if you talk to AI researchers, they will say, we have built this AI system, but we don't know how it works. That's the reason. Because we are not teaching the computers and telling them what to do. Rather, we are giving them data and figuring out learning on their own. So we don't know how they learned and what they learned. Right? So this was a paradigm shift. This was also a time when AI moved from the philosophy department to the mathematics department. Till this time, we did not even have a good definition of what is intelligence. And most of the discussions used to happen in the philosophy department. But once you had this notion of learning from data and probability and statistics, AI as a field moved more closer to statistics and computer science departments. Okay. The approach during this time, now all of you, I'm sure you have heard of this, is called data science. Right? So what was data science? The idea was that we agreed that we are not going to hand code the rules, hand code the logic, hand code the knowledge into computers. Right? Rather, what we will do is we will feed this machine data. But there was still the question of in what format. Right? So a lot of work that the data scientists used to do during this time was format the data in a certain way so that it was easier for machines and algorithms to learn. And this came to be known as data engineering, and a variant of that called feature engineering. So the data scientists spent their time engineering the right features so that machines could learn from data. Right? One example the example that probably appeals to most of you is think about your email inbox in Google, your Gmail inbox. Right? As soon as an email comes, machine decides whether the email should stay in your inbox or should go in the spam box. Right? There's an AI algorithm working there. What is the AI algorithm doing? Every email that is coming in, it is reading the email, it is looking at the words in the email, and then deciding whether this is spam or not spam. Right? So that idea of deciding that the way to look at, that the algorithm should look at words is a data scientist's job. Just to give you a little bit more flavor, a data scientist could equally say, along with looking at the words, I'm going to look at the sender email ID. That's feature engineering, deciding what to look at. Or it could say, I'm going to look at how many times previously has this person emailed me. That is a new feature. Or it could say, I'm going to look at the font that is used in the email body. Or it's going to say, I can look at what is in the subject of the email. So there are many, many ways you can think about what data to feed to the machine so that the machine can learn whether an email is a spam email or not. Okay. And once you formatted it data in a certain way, you gave this data to a set of algorithms, and the algorithms discovered whether an email or whether a particular email was spam or not. Right? And this is where data science really brought together the subject matter expertise. For example, the subject matter expertise that I was talking about, which is very obvious to us, that to determine whether a mail is spam or not, you should look at the words in the email, you should look at the subject, you should look at what is the font size, This is all subject matter. This is not obvious to machines. There is no way algorithms will be able to figure it out until you tell them. So there was the subject matter expertise. There was math and statistics, right? We'll show in a minute why. And then there was, of course, you have to program the computer. So this was computer science. So this is what was came. This was the era of data science, where we brought together these three fields to build several solutions, right? But the paradigm, the mathematical paradigm that underlined this era was two things, well, three big math subjects, right? One was, of course, probability and statistics. Second, I won't get into this too much, was calculus, right? It was invented by Newton. How do you optimize certain functions? And third was kernels, which is a field of linear algebra. And that's why if you see, those are three courses that all year one AU students learn in year one, right? Because those are the fundamental mathematic things that you need to learn AI. Now, the idea was that these machines will learn. Well, what does that mean? What do we mean that we'll give data to machines and machines will learn? Right? So the idea was that machines will learn relationships between the data. And in mathematics, relationships are captured using functions. So this era was about learning functions which relate one set of data to another set of data. Here are a few examples just to make it real. Let's suppose you look at a picture of a cat and you recognize it as a cat. We say that this is a function, because what you are taking as an input are the pixels on the image, and what you are outputting is the word cat. So this is a function, right? So if you have to build a machine which can look at an image and determine whether this is a cat, dog, human, or mouse, you are learning a function, right? So we call this function approximation, and this was the era of all the algorithms. For those of you who have taken it, data science, machine learning, all the algorithms that you saw in machine learning are different function learning algorithms, right? Of course, we won't go into them today. But the point to remember is that when we say that the machine is able to recognize a car or a cat or a mouse, understand that that recognition is very different from the way you and me recognize a car or a cat or a mouse. All the machine is doing is saying that this arrangement of pixels in an image appears most commonly in situations where the answer is cat. So it is learning how the pixels are arranged, and that's what cats looks like, right? So that was the mathematical framework that grew during this time. What was the limitations? They did very well. This era did very well. It has survived for 30 years. And even today, enterprises and businesses continue to use this. This is still not over. This era continues, right? One problem was that there was still a very significant dependency on the human data scientist, because the human data scientist had to figure out which features to choose, how exactly to configure the data, how exactly to structure the data before feeding it to the machine, right? So feature engineering was a key dependency on the human data scientist, right? So that depends on how good the data scientist you hire was. If he or she was good, then your models will perform exceedingly well. If they were not good, they will not perform well. The second problem was structured data. These algorithms worked very well on Excel sheets, spreadsheets, databases, but they did not scale for things like images, video, text, audio, right? Which did not have a very nice Excel sheet-like format, right? So that was the second limitation. The third limitation was that as you start trying to apply these algorithms on images, audio, text, video, these algorithms start to break down for several reasons that I won't get into today. But one replication of that was that the amount of data that you needed to train these models, especially if you were working with things like images, text, video, was very, very, very large. And to process that very, very, very large data, you need very, very, very large compute. So the amount of time it used to train these AI models was very, very large. Okay, that was the problem, and the compute power was, we were running out of compute power, and that was the limitation of this era. I had one more phase that I wanted to cover, but since we are out of time, we're going to stop here. We're going to pick this up deep learning, which is the next era that I wanted to talk about. And next Friday when I start, I will start with the deep learning era and bring you all the way to ChatGPT and 2025, which is now famously known as the post 2020 AI era. Right? I'll stop here.